Grade 12 Physics, Light Note number 4, Single Slit Diffraction. In this note, we're actually going to notice that an interference pattern can also be created through a single slit if we shine monochromatic light through it that's all in phase with one another. It's going to be an interference pattern similar to a double slit interference pattern, but there's going to be some differences between the two. One condition that we need in order to make this is that the single slit needs to be pretty thin. It can't be too wide so that the whole beam of light shines right through it. As we start to bring it closer and closer together, we notice that an interference pattern could be created. So here, if we draw the interference pattern for double slits, we know that there's a central bright fringe. Beside of it, there's two nodes, repeated by two fringes, repeated by two nodes, etc. We notice that all the fringes are pretty much the same width, the middle one being the brightest, and then the intensity dies off as we get further and further from that middle one. In a single slit pattern, that central fringe is double wide. It's double the width compared to if we create it through a double slit pattern. The fringes beside it get smaller and smaller, but they're still separated by nodes. So here the large central fringe, and then we have smaller fringes beside it as we get further and further away. That central fringe, if we take a look at it, is created by a lot of photons going straight through that single slit. If they're all going straight through and if they're all in phase, they're going to constructively interfere, and that's what's going to make a really bright fringe in the middle of the pattern. So here, if this is our screen, that's where our bright fringe will be. If we mathematically want to take a look at how this pattern is created, we're just going to arbitrarily pick some angle theta. We're going to look at waves that are going through that single slit. In this case, we're going to look at a wave going near the edge of the slit and compare it with a wave going through the middle of that slit. The slit will be of width W. If we compare the two waves, they're still going to have some path difference. And if we compare the top wave to one in the middle, if we're going to create that first node, the path difference here is going to be a half lambda. That will be destructive interference. The difference between this one and the one from double slit is we looked at waves going through each of the slits. Here we're looking at waves going through that single slit, and again comparing something from the top to something in the middle. If we look at some angle that's going to produce constructive interference, the path difference is going to be a full multiple of a wavelength, again if we compare that top wave with one going through the middle of the slit. So if we actually want to build some formulas based on this, we have to look at the general case when we take into account the whole width of the slit. So here, let's just arbitrarily draw a slit of width W. We're actually going to notice that if we take into account the whole width of the slit, destructive interference will occur for every path difference of a lambda, or any multiple of a lambda. We saw that destructive interference halfway was half a lambda, so that means the full width is going to produce a 1 lambda destructive interference. This means that constructive interference must occur for every half lambda, or every multiple of a half lambda path difference. Therefore, if we use a similar derivation method from the double slit interference pattern, we're going to get these two formulas below. The formula to calculate the location of fringes in a single slit pattern is going to be sine of some angle. It's going to equal n plus half lambda divided by the slit width. For nodes, we know it's every multiple of a lambda, so sine of some angle equals n lambda divided by W. We also get a derivation to calculate the distance to the node, in this case the first node, which will be y1. This is L lambda divided by W. In all three of these examples, W is the width of that single slit. So now what we'll do is we're going to use some of these formulas to try and solve a problem. Let's say in an example we have a single slit diffraction pattern where we're going to use green light, and in this case the green light is going to have a wavelength of 520 nanometers. If the width of the slit is 15 micrometers, and let's say the screen here is 1.2 meters away, in part A we're going to calculate how much distance is between the 5 central fringes. So if we think of that middle bright fringe, the 2 outside of that, and then 2 more, those would be the 5 central fringes. We're going to try and calculate the entire distance between those 5. In essence, if we're going to encompass those outer fringes, we need to calculate the distance to the third node. If we find that distance, we multiply by 2, and then we would have the total distance that would encompass all 5 of those fringes. So if we're going to find the distance here to the third node, we're going to use the node formula. So sine of theta to 3 is going to be n lambda divided by W. So we put in our values, making sure we have the proper conversions into meters. We find that the angle to the third node is going to be 6 degrees. Now, using the same formula that we used in the double slit interference pattern, we can try and calculate that distance to that third fringe using the angle. So here we're going to calculate for y3. We find that it's 0.13 meters. When we multiply that by 2, the total distance in that diagram above is going to be 0.26 meters or 26 centimeters. How far apart are the nodes? Well, let's just find the distance to the first node, and that should be our distance between all the nodes on one of the sides. So using that formula there, the distance to the first node when we put all of our values in ends up being 0.0416 meters or 4.16 centimeters.